Okay. I hope you have enjoyed your lunch, and thank you for coming back from the lunch. So first of all, stick with us because at the end of the second roundtable, we will have an important announcement, so don't run away. And with that said, so it's...
Actually, also do not run away because there is a cocktail served
Cocktail? Yeah. At 6 p.m. Yeah. Yeah, but the announcement too is very important. Not only the cocktail, yeah. Okay, and it's been a great symposium so far, very interdisciplinary, but now it's time to add additional dimension to it, so even more interdisciplinary. So we're going to add the computer science, AI dimension, but also the biomedicine dimension. So there is no better speaker than Michaela van der Schaar to take on this topic. So it's a great pleasure to introduce you. Welcome.
Thank you so much. Thank you so much for the kind invitation to come here and talk. Hopefully you can hear me, and hopefully the people online can hear me. You can't? Okay. Let me try one more time. Can you hear me now? Yes? Okay. So again, thank you so much for the organizers for inviting me. And also thank you for having this idea to have such a diverse and esteemed group of people together. I also need to admit, I was terrified coming here. So I thought I'm entering the lion's den. Statisticians, econometricians, pure mathematicians. I was thinking maybe I should invoke COVID and I should say I'm not available. But then as I was just about to do that, I saw Uri and I thought, okay, at least there is one more person to help me defend. Then during a break, somebody said, the machine learners who are doing this fast food. And I think it's a little bit true. So I'm guilty of it. So I'm going to give you some fast food. But what I hope is I'm going to learn from you. And despite the fact that I know there is at times some wrong antagony between statisticians, machine learners, I really think that we have a common enemy, and that appeared very, very, very clearly. And that is the complexity of the real world and the desire really to put our minds together to try to solve real world problems. And I think there's nobody more inspiring than Guido because he's combining the two. He's looking always at real world problems and bringing his very unique lens to it. I, on the other hand, usually am putting my hand like this when I'm looking at the problems I'm dealing with in the medical world, which is one important area where I'm trying to make a small contribution. But what I really hope today is to tell you a little bit of a machine learning perspective and get your comments, your feedback, and hopefully make a few collaborators among you. So I'm here also on a recruitment journey. Okay, so even though some of you may hate the machine learners, I hope you can agree that we have a common enemy, which is the complexity of the real world. Louder, louder. Oh my God.
Can you hear me? Yeah, I guess you need to talk very closely. Yeah.
Okay, let me try. Can you hear me now? Now you can? It's all? No. It's not on. Maybe we can elevate this if you have something. You see, even the microphone knows I'm scared. I prefer not to sit, so I like to stand. Thank you. Can you all contribute your laptops here? One more, yeah, wow. That's
1, 2, 3,
a
prova,
little
prova.
much. Thanks a lot. Hopefully you can hear me now. Works? Wonderful. But there is a second problem. I know most of you are here to hear pure computer scientist machine learner. The bad news is I'm an engineer by training. So not only you are getting to hear a machine learner, but you'll hear an engineer. And as a matter of fact, my perspective to causality is very much shaped by me being an engineer. So what you will see today is a machine learning engineering perspective. Okay, so what is really I didn't synchronize with Guido, I promise. It's unbelievable that he talks about panel data. I knew about his work, but I was not sure he'll talk about that. And what's interesting about it is my plan was also to talk to you about how to deal with causality when we have time series data sets. So we are talking about the same topic, so it's even more scary to bring you my perspective. So what I want to tell you, most of you don't need convincing as to why we should look at the time dimension, but if you are a machine learning crowd, quite a few people are not interested in time series data, so I'm going to give you a little bit of a motivation about why should we look at time series data, even though you don't need it after the discussion this morning. Then I want to tell you just a very few words about how I originally was approaching this problem from a machine learning point of view, very much inspired by work by Robbins and Miguel Hernan and all the wonderful work they had. And then I want to bring you the main core of this talk, which is going to be machine learning engineering perspective to causality, where I'm going to bring some ideas from dynamical systems and provide to you maybe a different perspective, hopefully useful on how to think about data. And then finally, I'm going to say just a few words about a few topics I'm excited about in the hope that I'll get more collaborators among you. Okay, so let me start by saying why would a machine learner look at causal inference in general? Well, there is wonderful and amazing work in statistics and economics for a very long time, so what does machine learning really have to add there? And my perspective is initially that there are two main reasons for machine learners to join this field. One of them is that we like to build different types of architectures. So we like to deal with complex data sets and try to learn from these data interesting complex representations that are presented. And maybe some of this would be useful for understanding nonlinear effects. Another thing that's important is often we have different ways to think about how to deal with treatment variable W, and we have a variety of learners. And machine learning has very unique ways to incorporate the treatment variable in the architecture. And we and others have looked quite extensively at that, and that leads to different types of trade-offs. Another issue, which I'm going to also touch a little bit today on, and already some of the questions came there, was really how to deal with regularization in general, especially when we have selection bias. So the work in machine learning started quite some time ago, and Uri, who is in the audience, very much started this work. And we were quite fast excited about this topic. So our lab has done quite a lot of work interested by a lot of real-world problems. So initially we stuck with the binary effect setting and looked at, can we model this as a multitask learning problem? Can we then look at deep kernel learning and introduce machine learning ideas to think about this problem? But then we migrated and started, driven by real-world problems, to look at other settings. What about multiple treatments? What about continuous treatments, which is very important, especially if you are interested, like me, in treatment effects in medicine and hence dosage. And maybe more recently, we were very interested in meta-learners, and even on how can we bring an automated machine learning perspective to causality? How can we, for a practitioner, help them select the best model for a particular data set? So these were some of the topics that have kept us busy in the last couple of years, and our work can be summarized in a few kind of subgroups of areas, and you can read more about it. But what I also am very interested as an applied person somewhat, I like to build cutting-edge machine learning methods, but I also want to solve real-world problems since I'm an engineer. So we wrote a few years back a paper which was more of trying to find collaborators in an area where people were open-minded, had data, and had problems. So we wrote this paper to the pharmacology community, and I was unbelievably positively surprised how open-minded they were and how much they were eager to accept a different point of view. So I was very fortunate to write this paper proposing some ideas, and then I got a huge number of collaborators out of writing this paper. So at times it's good to be courageous, so I hope the same thing will happen today. This was quite many years back. Now, more recently, we kind of supplemented that with another work. And also recently, together with Stefan and his group, we wrote a paper in Nature Medicine, which took quite a long time for us. This was quite a milestone because getting Nature Medicine to accept causal inference as, and causal machine learning, even worse, as a possibility to empower decision-making in medicine was a long journey for us. But with all that, I often get this feedback from clinicians, and I work with many clinicians in many countries, that the fact that all our work tended to be static. So we started to look at the cross-sectional data with treatments, and that was not very representative. And I have here a quote from Professor Owen McKinney, who is a clinician in Cambridge and a very close collaborator of mine. And I'd like to read for you the statement, not that you need a motivation, but I think this is really important, for me at least. It says, all problems in medicine should be considered time series problems. All our patients have histories, all diseases have natural histories, and clinical experience tries to capture these trajectories, but almost no formal methods exist to deal with this situation. Of course, this is the perspective of a clinician, but a clinician that also has a very strong mathematical background prior to him becoming a clinician. So it was very motivating to us. And what really he's saying in many of his talks is that currently they are guided when giving treatments to patients by clinical trials. Many of these clinical trials are enrolling non-representative patients and are focusing on average treatment effects and not comparing treatments. So it's clear that we need new tools to empower clinicians to make decisions on behalf of their patients. And the ideal type of questions they would like to answer are how to treat, when to give a treatment, when to stop treatment, when to change treatment, when to combine treatments. So these are all questions that are very complex, and currently, most of the time, this is an art more than a science for them. This is requiring a new way of thinking for machine learners. If you look at our huge machine learning conferences, I have the statistics, I forgot to put them on the slide, but in our NeoRIPS, ICML, likely our big conferences, there is only a very small minority of papers that looks at tabular data, and an even smaller minority that looks at time series data. And this is actually a challenge. So last year I gave a keynote at KDD, more or less saying time, the new frontier in machine learning, partially to try to make the machine learners enthusiastic about this topic. But what we are focusing on today is causality, the causal treatment effects inference over time. And usually we have data sets, like the one highlighted here on the left. And my initial attempts to apply machine learning for time series data with treatments was to treat it more or less as a deep learning problem, build representations, learn representations based on this data, and try to use that as decision support for clinicians. And very soon I've learned there are many problems with trying to do that. I'm going to tell just very briefly about that, but then I'm going to move to the last piece, which I'm very enthusiastic, is very much at the beginning, but this provides us a dynamical systems perspective, an interpretable perspective, and I think a powerful perspective to this problem. So it is really the last part that I'm going to focus in this talk. But I'm going to start with where I started my journey. I'm going to go chronologically. And I'll start with the middle panel. So what type of data? We are calling it often longitudinal observational data, where I have time-dependent patient features, time-dependent treatments, and I may have a static patient variable, such as genomic information. And this is often representative in electronic health records, and they encapsulate the patient history. What I'd like to do is use this patient history to learn heterogeneous effects from this data and empower clinicians for decisions that they need to make on the basis of this data. Of course, the problem is well known. We don't observe counterfactuals, and this is very challenging. So really very much our goal has been to estimate the potential outcome based on these historical features. And this is challenging in time series settings, as you very well know. And one of the many challenges are the fact that, as you see here, we have time-dependent confounders. So I may have patient covariates which are affected by past treatments, and then they'll influence future treatments. And this is, of course, all over this medical data. So dealing with these time-dependent confounders, it's a problem that we deal with in machine learning as well. The beginning, though, of my inspiration in this area is work by Robbins and Hernan. I stumbled upon this paper coming from machine learning and absolutely love it. So I read this paper and I went to my students and I said, oh my God, marginal structural models, and on the same, at the same side also the G computation, the G formula. We need to do something with machine learning on top of this. So I've done what many machine learners do. We put a deep learning method on top of it to look at nonlinear effects. So we built a recurrent marginal structural model that allowed us to really look at these nonlinear interactions and try to really build an architecture, a machine learning architecture that takes this historical data and tries to really forecast into the future, given all sorts of actions, what will come, what will happen. So make forecasts and try really to estimate in these ways what will happen, but also to try really to estimate potential outcomes. Now, when we did that, what we observed very early on was that both marginal structural models as well as our recurrent version of it were plagued by two challenges when we applied them to real data. One was that they were numerically unstable and they had quite a lot of high variance. So again, this is where machine learners come in. We said, okay, can we fix it using a particular new architecture? So something that is very popular in the machine learning literature is to come up with new types of regularizers and new types of ways to really discipline these representations that we learn. So rather than dealing with propensity scores, what we decided to do is to use domain adversarial training to really try to really discipline these representations. So what we built is a counterfactual recurrent neural network where what we do have is we have the past history of the patient and given whatever factual, of course, information we may have. And what we wanted to forecast into the future is what will be the effects of different potential types of treatments applied at different moments in time. And what we did here is we used domain adversarial training to adjust for the bias. So unlike dealing with propensity score weighting, this allowed us to be a lot more flexible. And by importing this idea, we were able to get better outcomes and estimate heterogeneous effects more effectively. But this, of course, remains a deep learning architecture, opaque, with all the challenges associated with it. Then we started to, in the fast food fashion, try to look at what's the next problem to solve. So we said, well, a big problem is that the data is not regularly sampled. And if you look at a lot of the architectures that emerged, we're considering data that was regularly sampled. So we started to say, well, how are we going to deal with this? Because this previous architecture is not able to elegantly solve this problem. So this is a challenge. And I'm not even talking initially about the challenge of the fact that these observations are informatively sampled. Even if I say, well, this is non-informative, I have data, and it's just measured irregularly, how to integrate it into my deep learning architecture. So what we did is we use kind of an innovation that happened around 5 years ago in the machine learning literature, was to use neural differential equations. So this is something that it was very powerful and was naturally dealing with irregular sampling. So what we did is we turned this into neurally controlled differential equations. And that enabled us to kind of have, again, this encoder-decoder architecture. But now, because we are learning using these neurally controlled differential equations, we are able to deal with continuous latent paths, and hence the irregularity of the sampling is no longer an issue. So, okay, problem solved, but we still have quite a lot of other issues. One of the issues that we knew from the very beginning is that this data is not missing at random. It is missing informatively. And we wanted to see if we can learn on the basis of the observations that we have. This is a problem that we looked much more deeply quite a few years back in a predictive setting, where we were able to show that in medical settings, but more generally in any area where the observations are informative, the experts know when they should observe and when they shouldn't observe a particular process, by moving from a Poisson modeling of this process of observation to a Hawkes point process, for instance, significant performance improvements could be made because we don't learn only from the data, but also the time that the observations were made. So we thought, well, could we do something like that for the setting where we have actions, we have treatments, and we realized the problem is a lot more challenging. So in this case, we really can't assume anymore that the observational risk is really the theoretical risk. And a lot of the work that at least the machine learning literature has done in this area was no longer applying. So what we ended up doing is trying to really model this problem. So we did something that often machine learners do when they don't know how to solve the problem. We tried to model as well as we could this particular problem. So we started to look at informative intensity functions for observations and wrote a paper about why this problem is difficult rather than solving it. So I really still need to solve this problem. So if any of you knows how to solve this problem, please reach out, because we have a lot of data where we have not only observations that are sporadic, but rather they're informatively measured. We know a lot about many challenges, and we wrote about that, but we don't know how to solve it, so please reach out. But I gave you this overview to show to you that, inspired by very powerful work in statistics, we try to really learn representations, moving from linear models to these nonlinear models, such that we can deal with more complex data and more complex settings. But three things kept bothering me as we were fast fooding through this literature. One is that in order to empower decision makers, such as clinicians, these models were not interpretable. Yes, we can tell you which features were important, but this is not true interpretability. Number two, the data that we had was sampled and, as I mentioned, at times informatively sampled, and we really didn't deal with it in a very beautiful and natural way. And finally, we were quite bothered at times by the assumptions made in the statistical literature, because we knew that they not always hold for the types of data we have. So we wanted to think, is there anything we can do to push a little bit the boundary? So this is what brought us to this new dimension. Sorry, before I talk about the new dimension, let me just recap more or less the assumptions that we often make in the machine learning literature. Here is work that kind of seeded this type of work in machine learning, including ours. And we have the kind of well-known assumptions: consistency, overlap, and ignorability. Yeah? Note, this is of course not for the static setting, this is for the longitudinal setting. And what's key in that is the fact that we have a treatment intensity process, lambda, and you can view this as some type of generalization of the propensity score in continuous time. So this is kind of the type of thinking, if you like, that we and others have adopted in this time series setting. And the reason we need these assumptions, of course, is to be able to estimate the potential outcome in this time series setting. And we couldn't have this equality without the assumptions that I mentioned. So, but we know often that this doesn't hold in a variety of data sets, including in medicine. So the question was, could we have possibly other assumptions than these ones? So this is kind of, this is 3 points: interpretability, the assumptions made, and the fact that the data was not sampled always according to either a non-informative or a regular intensity process. We are not having a Poisson arrival rate, kind of motivated us to see if we can look at it differently. And here is where an engineering perspective came to complement the machine learning perspective. And this is what I'd like to mainly talk to you about. So the goal we are going to try to achieve is to recover from this data, not a representation, but rather the underlying systems of ordinal differential equations, but I'll say a few words about partial differential equations, based on the observed data set. So what we are going to try to do is try to see if we can determine this system F of ODEs. And we are not going to try to do neural ODEs here. We are going to try to have transparent functions, transparent representation, ODEs. And what also we are going to try to do is we are going to try to personalize these ODEs. So we are going to have a general family of ODEs that is going to be useful for the entire population. But every individual in this particular data set will have an individual ODE associated with it. So this is, again, our attempt to deal with these 3 limitations of the machine learning literature. Okay, so I'm going to go back to these assumptions quite a lot later, but let me just say that we will need to make some assumptions, and the assumptions will look different, and I'm going to show to you how we try to reconciliate the old assumptions with the new assumptions, and why at times some of them may be liberating, and maybe why not in other cases. So we are going to have existence and uniqueness for these underlying differential equations, that ordinal differential equations that we are going to learn. So we are going to be able to say that the underlying process can be modeled by the system of ADEs for any initial condition. We are going to have observability, but observability in this context will mean something slightly different, which is that all dimensions of all variables in this ODE are observed for all individuals, ensuring that we have enough data and we indeed can recover that from the observational data. And finally, that each ODE in F belongs to some subspace of closed form ODEs. In other words, that indeed there exists some type of law, there exists some type of underlying, maybe complex, but there is some underlying law that drives this process, whether it's physiology, whether it's pharmacology, maybe it's macroeconomics, but there is such a law underlying it. Now, the first two assumptions, the existence and uniqueness and observability, play a crucial role for us to be able to discover ODEs from this observational data. And as I'm going to show later, there is some relationship that we have unraveled between our assumptions and the assumptions that we usually make in the treatment effect literature, the first two assumptions. All the assumptions, sorry. And what we're going to try to allow us to interpret the estimate as a causal effect. Yeah. We also have quite a complex connection of these assumptions, but I'm going to go about that later because right now it will be too abstract to talk about it. So I'm going to go to this later when I show to you what I'm actually doing. So let me start by taking a slight step back and look at a related problem, but a problem that has been challenging for us, the world, I would say, the community, not only of machine learning, but more generally for everybody interested in learning dynamical systems from data for quite a long time. So if it is to learn compact and closed form equations from data sets, this is very desirable, because it allows us to have interpretability, we can have generalization very easily, but also we can do all sorts of analysis. We can look at equilibria, for instance. So a lot of desirable properties appear if we are able to do that. And also human experts like to look at ODEs. We learn ODEs often now in undergraduate studies, no matter what subject we have come from. And if you look at machine learning, here I just put some examples to anchor ideas. So what I'm going to be interested in is ODEs and PDEs. And they abound not only in physics, but also in medicine and many other areas. And this is challenging because learning from observational data, the underlying transparent ODEs, has been a problem that recently has been started to be tackled with ideas such as SINDI and two-step symbolic regression, but they have still a lot of challenges. So what do I really want to do? I want to learn from, maybe I should put the problem here. So I have a data set of observations. Note that for now I don't have treatments. Even this problem is hard, and I'm trying to learn closed form ODEs that represent this data. What has been done so far? One of the solutions, and one of the only solutions that exist, is to do symbolic regression. But symbolic regression is conventional form, doesn't really deal with this issue because the time derivative is not observed. So what we end up doing in such settings when we try to apply symbolic regression, we do a two-step symbolic regression. And because this two-step symbolic regression is trying to estimate these derivatives, especially if we have limited data, we have noisy data, methods fail. So we don't have a good solution. And this is partially why neural ODEs, which are black boxes, have been invented. But neural ODEs not only are black boxes, have another problem. The fact that the true initial condition is unknown and is difficult to infer. So we have some observational data, but we don't know where the system really started. So even the black boxes that we have, like the neural ODEs, are having a challenge when they need to learn this black box from data. So lots of challenges. So luckily, I have a quite diverse team. Zhaoji is a statistician, Christophe is a mathematician. So the engineer, the mathematician, and the statistician, we started to look at this problem and try to see how can we really use observational data to learn this type of dynamical system, transparent dynamical system from it. And we built something that we call D-CIPHER that I'd like to briefly tell you about, because it's really at the core of a lot of the things that I'm going to present. So what we did is we wanted to circumvent this idea of estimating the derivative. So what we used is the variational formulation of ODEs that doesn't need to take into consideration the derivative of the ODE. And for that, let me just briefly, you have looked at the equations all day, so you can, I'm going to put one here. You see here that the variational formulation of ODEs uses functionals of the following type. This functional C, where you see the trajectory x, but not the derivative of x. What you see instead is the derivative of something different, derivative of g. But g is something that I can construct. And as an engineer, we love that. We always use basis functions and other tricks like that to circumvent hard problems like that. So when we saw this, we said, well, this is fantastic, because now I can convert this complex problem into a problem where I no longer need to compute the derivative of x, but rather the derivative of something I can build. I can build a set of bases that it's easy to compute the derivative of. So we used this variational formulation and prove a series of theorems where we are showing that indeed, if it is to learn correctly the underlying ODEs from data, what we need to have as a constraint is that these functions G that we are going to build need to be Hilbert basis. They need to be Hilbert basis, which is continuously differentiable and vanishing at endpoints. Quite a lot of basis functions can do that, including one of our favorites, the sign basis. And with this, we are then able to turn this problem in which we are trying to use observational data to estimate the ODE into a problem where we can just do an optimization where we replace these derivatives with these functionals. And these functionals now have embedded into them these testing functions. So note that we no longer estimate derivatives. We rather estimate directly trajectories. So problems such as limited sample size, noise, and also irregular sampling are no longer an issue. And as soon as we do that, we can use symbolic regression to learn. So this is, if you like, some of the fundamentals that we use to be able to build on. And then we also wanted to see, is this really working in practice? And I'm showing here just a few examples. And you will see that I chose a lot of examples where we have dynamical systems with saturation and growth. At times, chaotic systems, as the one that I'm going to show to you next. And we wanted to see whether indeed, if we have data that's sampled from this type of processes, of dynamical systems, are we able to recover the underlying dynamical system correctly? And we compare that against symbolic regression as well as neural ODEs to make sure that indeed this idea works. And in a set of quite extensive experiments, here I'm showing you a few, we saw that indeed this method called D-CIPHER is able to correctly identify the underlying ODE from which this data was sampled. And this is true if we have noise, it's true if we have varying sample sizes, it's true if we have limited number of samples. But this doesn't have treatments or interventions. Here I'm just learning a transparent ODE from data. What's good about it is also works when we have chaotic systems. And again, this is a challenge even for the black boxes that we have at our disposal, like the neural ODEs, because we do not need to solve, unlike them, the inverse value problem. So you see here that, for instance, a neural ODE is completely confused and is unable to deal with this situation. And we have many such situations in our data. We also try to see, can we learn something we don't know? What can we learn? And these are all the results from the original paper. Now we have learned new things that are a lot more interesting. But in this stage, we try to learn what are the mechanisms of evolution of disease for patients which have cancer, and how will their trajectory kind of change over time as we apply chemotherapy. And what you see here is, this is what we observe. This is one patient. I just highlighted one particular patient. And you see that things like Decode, our framework, our method, is able to capture this type of relapse, which we often see in practice, which we can't with methods such as symbolic regression, two-step symbolic regression. You also see that we get interesting looking equations and more simple than we would get with symbolic regression. Since then, this work is quite a few years back. Now we are able to learn pharmacological models from data, and we are debugging them together with pharmacologists. This is more challenging because here I'm trying really to look at the physiology of tumor growth, an even more complex problem. Two words about PDEs. This is even harder, and no longer I can do, so the question came during the morning session about not only time, but also time and space. So processes such as cancer evolve not only over time, but also time and space. And then we will have often an underlying PD that we would like to recover from data. This is true in medicine, but it's also true in age structure epidemiological models and many others. So it will be wonderful if we could learn PDEs from data. And we have no methods for that. So what we wanted to know is, could we have the same trick? Can we use the variational trick to learn PDEs? And the answer is unfortunately no. And this is even more complex to search, and the variational trick may not always work. But again, I have two secret weapons, Christophe and Zhaoji, and we conquered this last year, and this would not have been possible without Christophe, who is a pure mathematician, because we needed to invent some new math. I won't bother you with all the details, but what I'm going to say is that what we did is actually we looked at the existing literature initially, and there were quite a lot of limitations to how people went about trying to learn PDEs from data, including that often they relax this by making assumptions about linear combinations between the different terms, which we didn't want to make because we knew that much of our data may not have such assumptions, may not respect such assumptions. So what we ended up doing is we split PDEs in two parts. One is the derivative bound, and the other one is derivative free. This can be evaluated directly from data, and we don't need additional constraints. But this does require some technical constraints for the variational trick to work. So what we decided to do is we decided to define a very large class, a new class of PDEs, but it's a special class, which we call them variational ready. So this is a class of PDEs for which the variational trick does work. And we need to make much less assumptions than the existing literature to learn from that. And we have an algorithm that is quite sophisticated, that is able to learn from data the underlying PDEs. And again, we are happy because now we have tools in the form of Cindy, in the form of Decode, and in the form of D-CIPHER to go to the work that we originally wanted, try to learn dynamical systems from data that does have treatments and does have interventions. So let's go back to the original problem we started. Can we learn from data, this time with interventions, the underlying dynamical system and how it responds to interventions? Why would we want to do that? I was quite challenged by my group, which contains not only mathematicians, but also deep learners and machine learners. They said, well, why would we bother? We have already methods that kind of work. Why do we bother? Well, again, we need interpretability if it is to build decision support systems for clinicians, or for that matter, for anyone, and try to really understand the underlying process. We need to have, in my opinion, a natural way to deal with this irregular sampling, which we don't have right now in the deep learning literature. Also, often this Occam razor is at hand. Usually there is something underlying that's actually quite simple that may show to you how the system may evolve over time with or without interventions. And we wanted to learn that. And also the performance is not always great with existing deep learning methods. But there are also challenges. This dynamical system way was a very different way to learn from data, different than the machine learners, but also the statistical econometrics literature. The problem description was different, and we initially didn't even know how to deal with static features to incorporate them into the ODEs. Plus, for the problem to be really useful, we don't want to deal with just binary treatments. We would like to deal with the entire arsenal of continuous binary, categorical, and multiple treatments. So how to do that in the context of these dynamical systems? Again, I have more secret weapons. I added, in addition to Zhaoji and Christophe, an engineer like me, Sam, who helped me be a pragmatist, and Jeroen, who is a computer scientist. And together, we build this bridge between these dynamical systems and the world of causal effect inference in machine learning for longitudinal settings. How did we do that? I'm going to introduce to you these general frameworks that connects these two literature. I'm going to talk to you about the differences in assumptions and how we try to reconcile them, and where there are advantages and where there are not. And then we did, like we always like to do in machine learning, we built an algorithm such that we can go to work and learn something from data. So one of the first issues that we had was this difference in assumptions. So as I mentioned, the two worlds have very different assumptions, made roughly for similar reasons, but not exactly the same. And this was the challenge. But we also wanted to deal with the heterogeneity. So we have variation across these different subjects. And we didn't want to learn one ordinary differential equation, or ODE, for the entire population. We wanted to learn one ODE for every individual in this population. So how did we go about that? So first, we have new identification assumptions as opposed to what we had in the past, where we imported in machine learning roughly most of the assumptions that exist already in the statistical literature. So what you have is, on one hand, you have here the current assumptions that we make in machine learning, again, imported from statistics, of consistency, overlap, and ignorability. But on these dynamical systems, we have existence and uniqueness, observability, and I don't know whether you have noticed, because I didn't highlight it maybe enough, we make some assumptions about the class of ODEs from which we can select. This could be a very general class, B class, but we make some assumptions about that. So what we ended up doing is really trying to map this, and we can discuss more later if you are interested, but the consistency is implicit in the observability. The overlap can be relaxed by these two assumptions, 1 and 3, and actually this is an advantage. In this process, in this way, we have a less tough assumption than we have currently in the statistical literature. And this is an assumption that we feel more comfortable doing when talking to pharmacologists and physiologists. And finally, ignorability is quite similar to observability. It's not exactly the same. There are quite a lot of mathematical ins and bolts to make these assumptions. But this is kind of the rough map of the two. Then another challenge that we had was the fact that we really wanted to work not only with binary treatments, but we wanted to work with the entire arsenal that we often use in machine learning when we look at these problems: categorical treatments, multiple treatments, and continuous treatments. And what we roughly have is we have solutions now which are using piecewise OD, so we represent piecewise the OD depending on the situation we are at. And then to deal with heterogeneity and this between subject variability, we again needed to make different types of assumptions to be able to reconcile, if you like, these two words. I'll jump through the details of this because some of them are quite involved. Now that we made this bridge, we said, okay, it would be nice to now build an algorithm that is able to recover these equations, these ordinary differential equations under treatment from data. And we built this algorithm that we called InSight, which as a first step, discovers the population differential equation. And then in an inner loop, it discovers these patient-specific differential equations. And what's kind of important in this second step is that once the population differential equation is discovered, at times we discover it ourselves, at other times maybe we know by physiologists or pharmacologists, which is actually quite nice. So at times this discovery step is necessary, at other times is known already. What we do in our algorithm to do the personalization, we are fine-tuning the numeric constants to obtain this patient-specific differential equation. So in this way, we are able to model these individualized effects for the population, thereby being able to capture this between subject variability. Now, one question that came even in the morning talks was, what do we do really to regularize this? What do we really do such that we don't overfit to the population? So, well, we have a regularizer, as shown in here, that enables us to do that, the usual suspect, if you like. And this is key if it is for us to really learn effectively from data. We show in our experiments that if you don't regularize properly, you are not going to learn effectively from data. Now, what are really advantages of thinking in this way? First, after obtaining these patient-specific differential equations, you can go the other way. And you can derive a population differential equation that is governing this data. And each numeric constant of these personalized equations is represented by a distribution, which is, in other words, really recovering the probabilistic interpretation of the underlying data generating process that represents this data that we have. So we have now an interpretable, very clear way to think about this population from which this data set with intervention has come from. Now, there are limitations to this work. We're very aware. This is just scratching the surface. One is that a correct set of candidate functions is necessary for us to start the process. This could come either from an intuition of experts in this area, or we can use well-known classes to guide us. Also, the OD discovery works best in sparse settings. This is unsurprising. But to some extent, if it is to be usable, it needs to be sparse, because otherwise we give it to the clinicians and they'll have too many terms and it will not be interpretable anyway. So maybe this is not too bad. And finally, we are assuming in the current work that ODs are noise-free, but this is not ideally. So we are currently looking into extending this to stochastic differential equations, something we know how to do if we are black box, but we don't if we are white box. So what to do to make this, let's say, the cycle of discovery work? Well, ideally we have a variety of data sets that machine learners can use to really learn the structural equations that we are giving to the clinicians, which are the scientists, who can then validate that in the lab or in the clinic. And that could inform us, and we can continue in the cycle of improvement. But the reality is that these equations, something so complex as the human body, or for that matter, the economy, or you cannot have just very simple equations. So how do we deal with this problem? What we decided to do is, maybe this is a controversial slide I wanted to put here. We believe at least that if it is for us to really advance on this discovery ladder, we need to go beyond just causal relationships, at least causal relationships as looked in machine learning. So there is this Judea Pearl, which was a former colleague of mine at UCLA. We often used to laugh with each other because we are both in computer science department, and I was having the statistical dogma and presented the computer science dogma, and we'll often have interesting debates. But often, if you think about causal effect inference over time, just knowing, for instance, a causal graph won't be enough. You really need to know the underlying system and how it evolves over time. So this is why I say, well, maybe the ultimate thing on Judea's ladder should be discovering the governing equations. But how to do that? When we were trying to how to bring this to practice. And one scenario happened to us in COVID, because we are a machine learning group working on practical problems at times for clinicians. We wanted to know whether we can empower clinicians that deal with patients with COVID. And the data that often they have is very high dimensional and very complex. And what we learn is very transparent equations, very transparent dynamical system, but not with hundreds of variables. So how to really solve this issue? Also, the scientific models that we are discovering are often incomplete and incorrect. So how to bridge the world of scientific, if you like, understanding to the world of practice, the clinical world? And of course, the answer is machine learning. And I think that this is an idea of hybridization that could be useful as an idea that I'd like to propose to you all. So often, whether it's statistics, econometrics, or dynamical system, we discover very beautiful models, but the real world is much more messy. How to bridge the two? So to anchor ideas, we can learn, for instance, complex PKPD models or complex physiological models, but they are only as useful as you are in the lab. When you are in the patient, a lot more complex things may influence the dynamical system that is the human body, and also many things you no longer can observe. So in the lab, you can measure things like the concentration of a particular drug, but in the clinic, you can't. You may measure very rough proxy of this. So one thing that they measure often is C-reactive protein that tells you something about the inflammation in the body, but that could be due to many reasons. So how to deal with that? This is a real-world problem that was posed to me by my clinical collaborators in the Netherlands, who said, well, you are doing all this work on treatment effect inference, and we have a problem. We don't know how to dose dexamethasone, which was the first drug that was both in the UK as well as in the Netherlands given to patients with COVID-19 in the hospital. And this was a precision dosing problem that they really needed to solve. And they needed a pragmatic solution for that. And the challenge was, by experimenting, they saw that if they give too much, that led to issues. If they have too little, they have to issues as well. So they really needed to determine the dose to give to individuals. And this was a heterogeneous effect inference problem over time that was challenging. And again, it was challenging because they knew the underlying dynamical system. So in this case, they knew the PKPD model. It's very well understood. Dexamethasone is a drug that's very well understood for other diseases, but not for COVID. So the problem was not the discovery already existed. The problem was how to really use it now for something that is useful in recommending treatments. So what we did is we use the PKPD model, not invented by us. It's interesting because now we have models and ways to discover that, but at the time we didn't. So at the time we really used this PKPD model that existed and tried to hybridize it with the real world data to be able to make individualized predictions. So what we did is we have the expert model. We embed this into a deep learning model, a neural ODE, and it is this latent hybridization model that is making real predictions. This is an idea that's, I think, very general. So many of you come up with beautiful expert models, and these expert models may not take into consideration all the variables you have in the data or all the complex situation in which your model may need to function. I'd like to propose to you this idea of hybridization, which I think is quite powerful. Let's take the expert model, which can still be used for interpretability, so the experts could interact with it, but then embed this into a black box model that issues predictions, and thereby creating interpretable but powerful models through a process of hybridization. So just to show to you what was possible, first, often machine learning doesn't work very effectively when you have 100 patients, 200 patients, and we really needed to learn from very small data sets. Why were we able to? Because we didn't need to learn this complex representation learning that we do in machine learning, but rather we use these expert models to guide the learning. This shows the power of, again, statistical world or pharmacological world collaborating with machine learning. So what we do is then we issue predictions and forecasts. That's one thing that are very powerful. But we do something else in addition. We are able to use whatever observational data we have, which is the C-reactive protein, and through the latent hybridization model, we infer two things that are hidden, which the expert model needs. One is the immune response, and the other one is the dexamethasone concentration. And you see it here for two different patients. We did it for every patient. But what's interesting is you can't measure these things in the patient. Yet, this is what the expert model needs. So this may be an idea that will be useful maybe in other areas where you may have a beautiful model, just fewer parameters, some very well-crafted variables, but then when you want to use it in the real world, you may have other variables, and then you can unify them. So we did use this for some time in the Amsterdam Medical Center to make predictions, and you can read more about that. Now, I will, in view of time, not tell you too much about the next three topics, but I just put them here, if you allow me. One of them is, I'm very interested in what machine learning can do by joining forces with statistics and econometrics in clinical trials. And this is a very, very big area of interest for me. Another area that relates to causal effect inference over time is digital twins. We started around 9 years ago this work on synthetic data, partially because we couldn't share data, and the world of synthetic data has grown a lot. And digital twins, in my opinion, kind of combines these two worlds of causality with the world of synthetic data. And I'd be keen to talk to you more about that. And finally, I want to excite all of you about using large language models and combine them with powerful ideas in statistics and econometrics, because I think that really can help us make discoveries and understand a lot more than we do today. So they don't need to be just opaque black boxes or something to be scared about, but rather something that can be harnessed to empower us to do thorough understanding of the world we live in. Thank you.
Thank you so much. Thank you very much. It was a great, exciting talk. So now we can open the session for the Q&As. We are going to have half an hour. I guess we go this way.
Thanks a lot for the very nice talk. So I have a couple of questions. I can accept that if you have data which are generated by ODEs, which is actually your assumption, you are eventually able to recover the ODEs if the basis is sufficiently expressive, and that's fine. But I mean, when you face real data, you have fluctuations that matter, be them endogenous or exogenous, and then I think you can end up with fake representations of reality. I just try to make an example. So imagine you have a damped oscillator and imagine that you are shaking the damped oscillator with noise. And then the system will generate a resonant effect, and you end up with something which will look like a limit cycle. And then if you try to interpret this via the ODEs, you will end up with a model which is different from the one that you use in generating the data. So I think, the assumption of the uniqueness and existence of ODEs is very important. So I come from a physicist. I'm a physicist, so this is my background. So ODEs for me are okay when you are dealing with mean field models or thermodynamic limit, self-averaging or so. But when you deal with true data, fluctuations do matter, and it's really important to have them into the scheme. Then the other question, if I can put it together. Just a curiosity, so if you analyze the data over a finite time window, I guess that you will end up with an ODE which is sufficiently accurate within that, given the errors, within that time window. And then I think it's nice, the idea to be able to extrapolate equilibria, but I guess this is really hard, because I saw the model that you put up on the slide, x dot equal to some log t. This is divergent as t goes to infinity, so it makes no sense eventually, no? So if you can comment on these 2 points.
Thank you. Okay, answer. My guess is the questions will be all excellent points, and I agree with you. So first let me defend a little bit the first point. So in medicine, both in the field of physiology as well as in the field of pharmacology, often there is this assumption that there are these powerful equations that govern the response of the drug in the body, the response of the physiological system to these different stimuli. So yes, it's a strong assumption, but fortunately, this is an assumption which, to my surprise, currently a lot happens in medicine. So clearly in physics, some of these laws are a lot more powerful than they are in the human body. But again, this is very much what currently the science, if you like, of medicine is. Discovering these pure governing equations of the human body that may represent a particular organ or the interaction between organs. This is something that already kind of exists, and we are trying to power this work. It's true, though, that that's not always the case, as you very rightly say. So this is why at times we use these equations almost as the underlying science, and then we are hybridizing them with more complex data to be able to make forecasts. But what is interesting is currently these equations are discovered by pharmacologists, by physiologists in a quite, I would say, careful but not very powerful way. So fortunately, these communities are very embracing. If you need collaborators from some fields, I strongly recommend the pharmacologists. They're very open-minded and very keen to think with new tools and adopt new tools. So what we are able to show increasingly in partnerships with them is that many equations that they have used and currently are given to clinicians to think about a particular drug and the response of particular dose or the change in response to different types of interventions are quite inaccurate because their hypothesis space is even more narrow than what we can provide. So we are making together improvements. With respect to the asymptotic, you're very, very right about that. So this is why these piecewise representations, and we can have more discussion about that.
So, thanks for a very nice talk. You mentioned earlier on marginal structural models, and like you said, they're very nice. They can be unstable. And this instability property, right? It's easy to see why it comes from, right? When you have propensity score methods in a dynamic setting, you multiply these weights together, and your variance grows exponentially with the horizon. You also mentioned that you had a method based on adversarial training that could overcome some of these limitations. So I was curious if you could say a little bit more about applications where you used this method. and kind of what substantive aspects of the application your method uses to kind of get around the kind of fundamental difficulty of propensity score methods kind of in just generic dynamic problems.
Thank you. So, can I answer? Yeah. So what this domain adversarial training is doing, because we are able to look at entire trajectories now in the future, which we are going to try. So we have training data that we are using to train these neural networks, given different types of treatment, and then we have observations, factual observations for different time horizons. This enables us to really fit much better these nonlinear trajectories at these different horizons and kind of compensate for the differences that we see for the different individuals. So that allows us a much more refined way, if you like, to fit this data than we can with just propensity score weighting. And so we have a lot more degrees of freedom, if you like. Yeah. And you asked me for what we try to use that. So it's very unfortunate what we are using very often in our literature. There is a data set that comes from Harvard. Everybody who is in Harvard, big thanks. Which is called MIMIC, and which contains patients in the hospital with which a variety of interventions may be given, and we have factual outcomes for them in the short run, in the long run. So often what we do is we use this data set to benchmark our algorithms. This is one. This is more the real world data set. On the other hand, we also want to have a data set where we do know the counterfactual and we have the underlying, let's say, response. And for that, we are using a data set that appeared in a clinical trial for tumor growth and tumor growth over time. They are not ideal, I know so. But these are the two data sets that we usually tend to use.
Very nice talk. I was trying to figure out the slow food perspective, because for a statistician it's very hard to think about the existence of this deterministic function. For us, even the process which is behind the observed things is a random variable. So in some way, for us, there is one epsilon to be added every time. And so in some way, we can see possibly your algorithms as actually going after the expected value conditional on this covariate. So from this perspective, I think from a statistical point of view, could be more acceptable in that, because for us, the individual path is not identifiable without overfitting, because it's given from the signal plus the noise, every individual side. So we want to disentangle these two parts. So
yeah, so the data from which we, and I would welcome longer discussions with people about this exact topic. So 2 points here, I kind of made them, but not very clearly, I guess. One of them is the data is having noise, but we do make the strong assumptions that the OD is without noise. And this is why I mentioned one of the many limitations, but an important limitation is ideally we would like to have stochastic ODs. And that would deal.
From a statistical point of view, the individual path cannot be identified without repeated measurement.
You do have, though, these measurements of this underlying individual or body across time. And potentially now you would have information under intervention and potentially maybe without. Yeah? So often it's the same individual that has been supposed to these different types of forces. So I also would like to point out to you, in the paper we do make quite a lot of assumptions about noise and what assumptions the statistical literature will need to make to have identifiability, what assumptions we need to make. The assumptions are really quite different. So it would be interesting once to sit down with somebody that's very deep in this area and discuss them.
So thank you very much. Very fascinating. So question from an economist. So typically we would have aggregated data over time, right? So which can potentially help you with the noise issue. And I was wondering whether you thought whether this framework, which explicitly allows for aggregation over time and the functions that you use, right? The testing functions. But still you apply this to the sampling that's at a point, right? So have you thought about doing this for aggregated data? Because I think that would be more natural for many types of data that we have.
Yeah, interesting. No. No, this is very, very kind of, for us, fresh work. There are many things we feel that are possible. Yeah, keen to hear more thoughts. The only thing that we do, as I mentioned, is that we have at the end, we get this perspective where we learn these different individualized ODEs, and we kind of try to learn this joint model. And yeah.
Thank you very much for the exciting talk. I'd like to come back to Stefan's question, if that's okay. So it sounds like instead of going for the IPW representation of the estimate, you're going for the G formula.
Yes.
So that's my first question.
Yeah.
And if so, against what function classes is your approach robust to? You're using this adversarial approach. I assume that there's an assumption about the function classes that generates the outcome. If you could please speak about it.
Thank you. I talked about two classes of work, I would say. The last one, where we learn this ODEs from data or PDEs from data, doesn't use the G formula and doesn't go in that direction, yeah. But we do assume some function classes for the ODEs, the family from which they may come from. And that assumption is restrictive, but we are making that assumption. The function class is often it could be quite broad, and it can be informed, for instance, by knowledge from pharmacology, from physiology. But if you look at the other work, the original work, which was very much inspired by work from Robbins and many others, there actually we learn this deep learning representation, yeah, that is useful for making forecasts and predictions, but we don't have anything more than just uncertainty estimates associated with the predictions. So the only type of, let's say, uncertainty quantification, the only type of guarantee that we can give is in the form of either credible intervals, or we have some version of it where we are using conformal prediction over time to tell you how really accurate these different models will be, but nothing more strong than that. But I would be keen to learn how to do it.
So sorry if I'm slow, but can you clarify what you really mean by estimating or the individual treatment effect? Because as a user of causal inference method, if I think about the Holland's 86 paper, there is a fundamental problem in causal inference. Can you explain how you solve that problem?
Yeah, I should be very careful. I should say, this is the disadvantage of being fast food. So we often use this word individualized, even though it should be conditionally average treatment effects, partially to make this bridge to personalized medicine, individualized medicine. So this is part of the goal. And a similar attempt, so in the early part of the work, should be conditionally average treatment effects. In the last part of the work, we are indeed trying to find OD that's personalized. and we try to find individual initial conditions that are individualized to this particular person. So we are learning not an average, but rather a personalized equation for everybody in the data set.
Because the initial condition are big, not the shape.
Yeah. So this is indeed. So we are kind of saying the physiology would be the same for everyone. Yeah.
Thanks. This is a very interesting talk, and this is why it's so nice to have these interdisciplinary conferences. I particularly like the part about these irregularly spaced observations, and that in fact they may contain information about what the underlying processes are. One just practical question: what are the magnitude of the data sets you would need for estimating these models reasonably accurately? What is the order of magnitude there?
So let me decompose this question in two. So the first time we looked at longitudinal data with informative sampling was not for anything causal, but rather just for making forecasts, so time series forecasts. And part of the reason we started to look at that is that our data sets were relatively small. So this was when I was still at UCLA. We had an electronic health record that contained at the time, for the patients of interest, around 1,000 patients. 2,000 patients was not enough. So we wanted to learn with all the data we could get our hands on. So this is the moment when we started to look at this Hawks point process to model the intensity of the data acquisition, and that provided a lot of boost on top of the Gaussian processes which we were using at the time. You can see that this is in a different era. Now, when we looked again at this problem, we looked with data sets which were in the order of 50,000 patients, so a lot more patients. This is very interesting because we have patients for which you may have 20 observations, and some for which you may have thousands of observations. So it's another issue associated with this data, and to learning this ordinal differential equations from data. You have people, for instance, in the hospital who are there for months, and people who are coming and going. So this is another big challenge associated with learning this correctly from data. So again, if anyone knows how to deal with issues like that, please reach out. Because the doctors know very well, if they give a treatment, kind of what will happen, or what they expect to happen. So even the measurements say something about their expectation about the potential outcome. At other times, what's also interesting is that there are... Yeah. At other times, it's interesting because you have observations and then you see that they change the treatment, which is also interesting. So they know something about the current treatment as opposed to the new treatment. It seems to me something interesting to learn from expertise and expert knowledge. And this brings me to another point that I didn't bring in this talk, but we are looking a lot at, which is the data set is not, it is captured on the basis of interventions given by experts. This is what we assume. So we assume that the clinicians knew when they gave a treatment, when they didn't give a treatment. This was not just random observations. So there is still quite a lot of variation in practice. So how to take into consideration these different levels of expertise in the assignment? Yeah? Because, again, treatments were assigned with this different level of underlying expertise. At times we may know something about that. How can you use that to improve the whole process? Yeah.
Well, thank you for really incredibly rich talk. I really enjoyed it. I want to ask you a little bit about whether this approach has inspired some theoretical work. I loved your setup saying, functions implicitly defined, ordinary differential equation, partial differential equation, the problem gets harder and harder. What are the theoretical work in terms both the complexity issues as well as these theoretical foundational issues like whether the inference is even possible, what assumption you make, identifiability? It's a more kind of statistical question, but I see is these kind of thinking, the machine learning thinking, which I think one thing statisticians really did not do is getting to the partial differential equation part, right? Because we don't do much of that. But has this empirical work inspired theoretical work so we have deeper understanding of the limitation of this modeling and how far we can push?
The answer is no. I hope some of you are going to volunteer to look at this, and we have tons of problems that we hope you are going to help us solve. We are happy when we have an algorithm and it works on the data. We feel it works on the data, and we beat a benchmark.
Hi. In the discrete time longitudinal case, I found some similar work that tried to combine weighting with representational learning. So instead of using as a substitute, combine them together with some form of regularization. Do you think it's promising, or like do you see propensity score as an alternative to representational learning, or they have some they could be used together in some positive way, especially in the continuous case, and also in general?
No, I think that this is interesting, and I think that there are still a lot of things to be thought about. I didn't talk here much about another avenue of work that I pursued for some time, and then I got stuck. I didn't know how to deal with it further, which is the dynamic treatment regime setting, where, again, machine learning and ideas from both statistics and reinforcement learning were combined to try to deal with this dynamic treatment regime. That's just another area that could benefit, if you like, from this. I think that all of this is very exciting. What I see in my own work, because I'm very interested for somebody to really find this useful and do something with it, I'm very keen to collaborate with these physiologists and pharmacologists, and for them to validate these equations, to think about these equations, to think about these systems. So it's absolutely needed to have transparency. And since they like to think about ODs and PDEs, it's very natural. But I think in many other cases, this is not needed. And I think it's an opportunity to take powerful, clean ideas from statistics, econometrics, for which we have identifiability, learn something truly causal, and then embed this, that's the reason I put the last work, embed them into some type of machine learning approach where you maybe no longer have the science, but you are embedding the science into something that becomes very actionable and very powerful. So I don't know whether your question was, maybe I misunderstood.
Also, in the space, I was thinking also another thing, that the overlap assumption is often fairly strong in a longitudinal
Yeah, this is exactly. Yeah, so I couldn't agree more. As a matter of fact, I wrote a piece which I never put online. This overlap assumption for time series is very, very unnatural in many settings. So this is why for this particular last work that I mentioned, we have slightly different assumptions, which I think are much more natural. So it is very much because of this overlap assumption, which I think is very okay in the cross-sectional setting, but much more challenging for the time series setting, that we came with this new perspective. It was very much a reason for it. We're keen to talk more about that.
Time for one last question.
Thanks, Mihaela, for a fascinating talk, as usual. So just one question about ignorability. I know how to think about ignorability. I can know what questions to ask. How do you think about observability? Like, what should I think of when I'm trying to assess whether that assumption is reasonable or not?
So in other words, kind of more or less in the first question, I need to have a rich enough observation about this dynamical system, given its complexity. and to make sure that indeed I have a long enough or sufficient trajectory to learn. You are talking about the last piece of work, yes, the dynamical system. Yeah. So there, the advantage is again that we have data sets that are collected by pharmacologists who often think about this as a dynamical system problem, and they on purpose capture data sets that they believe, given their knowledge of physiology, given their knowledge of these effects of these drugs, the long-term effects, they capture this information. So quite a lot exists that we can kind of import when thinking about observability for our setting. The only difference is that in their case, they may do that more or less based on tools that exist, if you like, and they use certain types of compartmental models with different types of structure, while in our case, we can really learn from scratch this information. Yeah.
If, for example, my clinical partners tell me I treat according to this covariate and I don't have this covariate, then I know it fails. Is there like some very explicit failure case for observability that you say, okay, well, here it really doesn't hold, don't try? Is there an example of that?
So, for instance, if you know that this particular drug is going to stay in the body for a certain amount of time, and I don't capture that, it's a good example for it. So what I'm trying to say is that we are piggybacking to some extent on some things that they already assume when learning these models. This is why we feel slightly comfortable to learn from the same type of data. So very, very recent work trying to learn for warfarin a better model than what they have. They knew the time scales, they know the responses, and we inherit that.
Okay, let's thank Michaela again. Thank you very much. Sparring talk.
Okay, hello. I think we can start the next section. Okay.
I wish.
Hello. Okay. Let's start. Stand up, huh? Okay. 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 Good afternoon. We are here for the last session of the day. It has been a long day. A lot of thoughts, good speakers, interesting discussion. And then we have a last one. So my name is Pietro Ferrari, and I'll say a few things about my background, although I was not supposed to talk about myself. I was here to chair a session with Julie and Michaela. Raffaella Campaner for University of Bologna, she is sending her apologies. She couldn't be here today. So because I had a little bit of more time, I decided to put up a few slides telling you about who I am and what I'm doing. So I'm leading the Nutrition and Metabolism branch at the International Agency for Research on Cancer, which is a WHO institute based in Lyon in France. What we do in the Nutrition and Metabolism branch is we have a strong focus on cancer prevention. We also have ambitious ideas to investigate candidate mechanisms of carcinogenesis, and we do that with a wealth of lifestyle, nutrition, and molecular data. Molecular data spanning from biomarkers, but also omics data, including genetics. And clearly these are challenging data because there is a lot of behavioral information, and then they suffer from three main weaknesses. There are a lot of confounding, as anything behavioral, large amount of exposure misclassification, and reverse causation. And I could say that historically, I would say cancer epidemiology has been putting out a lot of papers claiming, I wouldn't say causal relationship, but without making it clear enough that at best, estimates coming out of observational studies were associations or correlations rather than estimates of effects. And so is a day-to-day challenge for people like us to not only correct that false messaging, but also to find ways to assess causality in what we observe. So I was asked to chair a session on causal discovery in genomics, and then was looking for definitions, and then we could agree that this is the process of identifying and understanding causal relationship between genetic factors and biological outcomes. Could be a disease, could be other traits. And an interesting aspect here is that when we're talking about identification of genetic variants, we could directly link those to a specific disease, but we could also link genetic variants to exposure. And I'll come back to that in a second. Apologies, this is a Mac PC incompatibility. But so there are a number of methods, and I think here, I mean, that the audience is well educated on any of them. What I like to stress is that the causal mediation analysis has been a step up in observational epidemiology because in observational design, because has forced people to think about a confounding structure in a serious way, in a very formal way, and this has been useful. Mendelian randomization, as well as interventional genomic, we don't work with the last one, but we work quite a lot with Mendelian randomization. And this is a good example where we're looking for instrumental variables that could predict exposures. And then standing assumptions, we can infer causality on the relationship between exposure and a disease. And we do that with quite lot of data coming from individual level studies and genetic consortia, given that a lot of GWAS information is more and more available. I like to put up this one because this is something that I acknowledge the limitation of observational designs, and there was an interesting comment by one of the persons in the audience with a pink shirt. Stressing the fact that a lot of audience, a lot of audience here is quantitative, and then we utilize this principle of triangulation. And then I was looking yesterday, I didn't know about it, but the first idea came up by this Patton and published a paper at the end of last century on enhancing the quality and credibility of qualitative analysis. And then 15 years later, there was this other paper on the use of triangulation in qualitative research. And then I find this interesting that Debbie Lawler from University of Bristol, by the way, is the same group that put up the ideas of Mendelian randomization. So this is together with George Davis Smith. So they were thinking about that a good idea to, I would say, acknowledging the limitation of individual evaluation of scientific evidence. It would be to combine evidence generating from multiple designs, multiple data, multiple statistical technique, and of course also by different people. And as a matter of fact, I'm doing a little bit of publicity to my own institute. This is not work that I do. But one of the activity of the International Agency for Research on Cancer is to assess the causality of exposure agents or chemical agents. And they have been doing triangulation way before this was formalized in papers. Okay, so this was my short introduction. I'll give you the floor, Julie. Non vedo il mouse. No, perché non so come metterlo. Does anyone know how to display PDF? PDF is Control L. But you need to first click with
Okay.
Control L funziona.
You need to take it off, the split in video of them.
I don't want to split the video, I want to mirror.
Okay, so thank you. So first, I would like to thank the organizer for the invitation, because it's really an honor to be able to discuss causality in such a beautiful and inspiring place, and with such an audience. So before starting on the topic of the roundtable, just a brief presentation of myself. So I am Julie Josse. I am a senior researcher at INRIA, which is a national research center in digital science in France, as you can guess. And I lead an INRIA INSERM team. So INSERM is a national center for biomedical research and human health. And the name of the team is Pre-Medical, for Precision Medicine by Data Integration and Causal Learning. And this is a team which is composed of researchers in machine learning, biostatistics, but also clinicians. And we also have PhD students in statistics who hold a medical degree. And for me, this is really crucial if we want to transfer the methods we develop for a better adoption of the method we develop, and as well as for innovation. So as the name indicates, we do precision medicine with causal learning, but also with federated learning, also to ensure the privacy of medical data. So concerning my own research, I mainly focus on developing methods to handle missing values, because often I work with data which look like this one, where I will have patients in different hospitals that can be described by some features, so for instance, clinical data, biological data, questionnaires, and I often have missing values that can be sporadic. If I have for one patient, I have one feature which is missing. Here, missing values are represented with NA for not available. But we can also have systematic missing values, where you have one whole feature which is not available in one hospital, or for one patient, I have clinical data, but maybe I do not have the biological data. And so I develop method whether to do inference with missing values, matrix completion, or supervised learning with missing values, and also causal inference with missing values. And on the causal inference side, I mainly focus on combining RCT and observational data, whereas to better estimate heterogeneous treatment effect or to predict the effect from an RCT to a target population. And currently, I am deeply interested in federated causal inference and meta-analysis. Oh, yes. And finally, multidisciplinary projects are at the heart of my work, and I just want to mention one project, which is the Traumatrix project, which fits well within this precision medicine topic, because we have built a clinical decision aid system to improve the care of trauma patients. So trauma patients are patients with hemorrhagic shock and traumatic brain injuries who require specific care in what is called trauma centers. And so our objective was to build a decision aid to reduce over and under triage of these patients. So basically is to send them to the appropriate center for better resource allocations and anticipate the resource needed, such as the blood resources. And this is a very mature project because we will launch a clinical trial to assess the models we have implemented in real time. It means that before the end of the year, in the half of the French ambulance, we will have mobile data collection applications, and that will predict some outcomes. So when the organizer told me about this roundtable, to prepare this roundtable, they sent me 3 papers from Mihaela. So I have read this paper, and in particular the causal deep learning one. And I am going simply to select quotes that I have caught my attention. I will give my reaction, and I am interested, of course, in hearing your thought and maybe your solutions, because I will raise issues and I am not aware of all the solutions. So the first quote was, a big part in a researcher workflow is to identify gaps in the literature. And while I fully agree with this quote, and I participated in this, I would wonder also if a big part of our research should be dedicated to consolidate the methods that we have in the field. Because in a way, I feel that there are many, many methods, many, many papers, and consequently, it leads to an overwhelming number of choices for the user. And the user can be completely lost in this multitude of options available. And one consequence of this is that it may have an impact, it may explain why there is such a gap between theory and practice, and why many theoretical advancements do not translate effectively into practice. And maybe one way to reduce this gap between theory and practice is through software implementation, but we need to go beyond just releasing code on GitHub, which is often done. This is nice, this is a first step, but this code is never maintained, and the aim of this code is not at all to be used in the long term. So to have sustained software, it's maybe a matter of incentive, and this is not necessarily easy to have this. In the same thing, speaking about incentive, if I want to write a grant saying that I want to consolidate the available methods to help the user, I think it may be a bit difficult to get funding, whereas it may be easier to say that I will design a new personalized medicine that will revolutionize personalized medicine. So to illustrate the points why the user can be lost, I will use 2 examples coming from my research. So the first one consists in estimating an average treatment effect. So it is to assess the impact of a drug, tranexamic acid, so it's a binary treatment, on an outcome which will be a binary outcome, mortality at 28 days, and I have some covariates. And to assess the effect of my treatment, I am lucky because I have access to a huge randomized control trial in blue, and the results that we can show here shows that I have a negative average treatment effect, and because I use risk difference, it means that I have a slightly beneficial effect of my treatment, using the result from the RCT. Then I also have access to an observational data, that is the trauma base, that's to study this same question and answer the effect of tranexamic acid on mortality for my brain trauma patient, because this is a drug which aims to reduce bleeding, and usually it is used to reduce external bleeding, and here we focus on internal bleeding. And when we look at the result in pink for this in purple for this observational data, basically I see a slightly positive average treatment effect, so meaning that I have a slightly deleterious effect of my treatment. So this is not necessarily surprising, because you may have different populations, and if you expect heterogeneity, that your effect of your treatment depends on some features, this makes sense. But still, if my target population is this observational study, I see, okay, I maybe have a slightly deleterious effect. To make this conclusion, I have done some assumptions, and I can also use other methods to try to target this quantity, the effect of my treatment on this observational data and this target population. So I have used generalizability method, where I try to transport the result from the RCT to this observational data. And of course, these generalizability, transportability methods, they require other kind of assumptions. And the results are displayed in pink. And here, it's a bit less clear what I will say as a conclusion. So maybe I will say that I have not really evidences toward like an effect of this treatment, and maybe slightly different. So here I have presented maybe 10 different methods, because I have used outcome modeling, weighting strategy, methods that combine both. But of course, you have much more. I can put a lot of different box plots, because I can have the choices of the learner, which learner I'm going to use, parametric, non-parametric. And in addition, when I work with the data, I have a lot of issues which will make me creating other methods, because when you combine both data sets, you may have, as I mentioned, features that are not present in both data sets, like feature mismatch. You may have also missing values in your RCT and in your observational data. You may wonder which covariate to select, because I may want to add some covariates maybe to improve the precision, but maybe there is a trade-off. If I use non-parametric methods, maybe I need more data. And in addition, I measure my causal effect with a risk difference and not necessarily with other metrics. So my point here is that although I find this method very promising, because you can generalize in other populations, I still think there is a huge gap, and a lot of research is needed before this method could be safely implemented in practice. And in addition to creating other methods, the point will be also to create maybe more benchmark, more guidelines to help the user navigate it with all this. And I take the opportunity just to comment a point made by Liz Stewart on how we do with both quantitative and qualitative, because usually when I deal with this, what I will do is something a bit, I will aggregate a bit everything, saying like, oh, if all the method points to this direction, plus given the plausibility of the assumptions that I discuss with the clinicians, maybe I tend to think that the evidence is slightly a deleterious effect. But it's a bit very qualitative and not very formalized, but this is how I proceed in practice. So the second example is in policy learning, and in policy learning, this is a very simple example of policy learning. I have a continuous outcome, I have categorical covariates, a categorical treatment representing different doses, and then I have some covariates. And I just want to find, in a way, which dose to give to which person. I can use policy learning, and there are so many methods to estimate your policy based on outcome modeling, on classification. There are so many methods to compute the value, to estimate the value of your policy, plus the choice of your learners, plus the fact that I need to deal with missing values, that I often end up with this kind of plots where I have a value here computed by AIPW for different policies. And I look at this and I say, oh, maybe if we take the policy which gives the highest value, it can be something given by multi-arm causal forest or by weighted classification. So I take the opportunity to thank Stefan Wager for all the work he has done for the GRF package that I use on a daily basis with my clinicians, and which is a sustained implementation. And so, yes, I can say, like, okay, maybe I will have a look at this policy and maybe select this policy, because the aim is really to implement this in practice, so you need to make some choice. And if I look at these two policies with the same estimation of the value, and I look at the individual decisions, then I can have very different individual decisions. So here I have represented Sankey plot. So on the left, I have the initial dose, so initial categories of treatment given by the doctor. And on the right, you have the doses given by your policy. And I have just represented two policies leading to two different recommendations. This can be explained because we can have the same value, but still completely individual recommendation. But this is a bit confusing for the user. So yes, okay. At some point, say, okay, what I'm going to use in practice. So maybe there is a need for more research, maybe not to output a single category, a single treatment, maybe a set of treatment, plausible treatment, and maybe this approach already exists. So a bit more on quantification of uncertainty can be useful to help navigating with this. In addition, we also need to be aware that the methods we develop are then sometimes implemented, and you can find very implementation in different software. And my colleagues were working with Python, so we have worked one policy learning method implemented in Python in the Econ ML package. And in fact, I think it was not well implemented at all. It gives a policy that never recommended recommend a dose that never matched the one which was recommended by the medical doctor. So this is a bit suspicious, and you don't want such a policy. It will be difficult for the medical doctor to adopt this policy, and you do not have support in your data to estimate this value on the policy. So yes, I think Miela can react after that, because I know that you have some work also on what to do with all these ways to estimate heterogeneous treatment effect. So I will go quicker on the other points. The other points is that I think we still need to encourage people to think carefully about the design and about which data should be collected. This is really a point that the causality community is aware of, because we spend our time saying, oh, it's not a sample size issues, but you need to collect the appropriate data to separate correlation and causality. But I feel that for personalized medicine, often I may miss a lot of information that may help me to suggest the appropriate treatment. I have example, for instance, in vitro fertilization, where we try to find an optimal dose of hormone to maximize the size of oocyte. And I just have clinical data to say that. And I don't have, for instance, psychological tests of women, which may be very important for such cases. And when I work in oncology, often I also have a lot of clinical data, but when you have a severe disease, the patients are really willing to try everything to improve their condition. So they are going to have dietary supplement, other medicine, and so on. And this kind of data is never collected, and a lot of clinicians think that there are a lot of possible interaction and also possible impact and importance of taking this into data. So my point is more just to still encourage people to collect data and to question the data collection. And to collect the appropriate data, this is only possible if we have, like I quote Miela, a clear communication between like researcher and the application domain. And I have really countless of examples where through discussions I have really understand how the data were coded. And it has an impact. So for instance, I have seen like distribution changes in gravity score due to funding, which is tied to the severity of the patient. I have missing values sometimes just because the team are not in agreement, that do not want to share their data. People can go to a specific center or hospital just because, in fact, they trust the reputation of the clinician in this center. And all this information, we know that we do not have this necessarily in this data. So this is us work to work with missing information. But sometimes this context helped me really to better code the data and interpret also the result. And the context for me is also crucial to assess all the methods we develop, because I need to understand who is going to use the methods, for who are my, it's not really who are my customers, but this is important also, but this is really who is going to use it, what is the impact of the method that I develop, but on all the stakeholders. So finally, because I have focused on this causal deep learning paper that I enjoy, because it was a bit more like guidelines and philosophical things, still I think that we need to, as a researcher also, to say when deep learning is useful or not necessarily useful, because in a lot of clinical data that I use, in fact, with random forest or gradient boosting, it's perfectly enough to take into account nonlinear relationship. And it's important also to preserve the energy resources, so not to use too much when it's not needed. And finally, because it was a causal discovery and precision medicines, I do not have a lot of experience with genetic data, neither causal discovery. But still, I use DAG with the clinicians, and often this DAG, just to understand why they do some information, what can impact the outcome, are completely given. Like what they do is that they organize what they call the Delphi, so it's a consortium of clinicians as they gather together to produce this DAG. And this is really nice because then I have a DAG from an expert and I can start working, but often this is not questioned at all. And I use it without doing a bit of sensitivity analysis to the DAGs that I have, neither also to think about maybe there are algorithms that may be difficult to scale, but maybe we can have a bit more interaction. So this is more a call to see how people do to do this. So thank you.
Okay, maybe Michaela, do you have, maybe you can start either with some reflections or questions for Julie.
Yeah, thank you. So maybe I should say this reflects also the different communities we are in. 3 points there. So why did we write this paper on causal deep learning that Julie refers to? First, and I guess Uri, who is there at the back, the other machine learner in the room, can sympathize. We tend actually in the machine learning community to be very benchmark driven. So we usually have somebody that has a particular data set and has introduced a problem. And everybody is trying to beat that benchmark by coming up with a better algorithm. So there is an explosion in machine learning of certain benchmark and everybody trying to beat the benchmark, and we just focus on those problems. And part of what I try to do with this causal deep learning and what I try more generally is to encourage people to go and look at real world problems that need solving. And one of the things that we wanted to do was a little bit similar to Guido actually for his field, but in my case, for my field, I was saying that everybody is looking at causal inference in machine learning for the static setting, cross-sectional setting, and not enough people to the time series setting. So part of the reason I wrote that causal deep learning manifesto was to tell people, let's move to the next frontier, which is time. That's one thing. The second point, I resonate tremendously with what Julie said. I think she is very right. And in machine learning, I would say it's even a bigger deal than in statistics or econometrics. We have an absurd amount of machine learning methods and algorithms that try to solve that particular type of problem. So we have a lot of them. So how do you choose among them? So the way we usually tend to think about that in the machine learning community is through automated machine learning. So what we do, for the ones among you may not know about this field, I'm quite active actually in that field as well. We are trying to have machine learning, the user coming to the machine learning method and machine learning selecting the algorithm to use for that practitioner. And that is wonderful, works quite well. But for causal inference, of course, one of the biggest challenges is how do you select the best model depending on both the metrics, but also because you don't have counterfactuals. So there are different ways to think about that. I'd be quite keen to have a subsequent discussion. The way in which we currently look at is either by using influence functions and trying really to have a way to compute and estimate these counterfactuals and try to recommend methods for a practitioner. The other way is the unthankful way, which is exactly kind of Julie said. We decided together with a few collaborators from Belgium to spend a tremendous amount of time to build a quite big software package for machine learning causal inference, such that there is under one Python package, all these methods are available to you with all the comparisons and everything under the sun. We are just about to release that package. And the only reason we could do it is because in Belgium, unlike in UK, PhD students are a little bit longer, and the student at KU Leuven will be more time to not only complete the thesis, but also a very nice package associated with it. So, yeah, I couldn't agree more. The jungle of machine learning is even bigger, and the divide to econometrics and statistics is even bigger because at times you use R, we use Python. We try to bring quite a lot of famous methods into this Python package, including causal forest and a few others. So this package will be available relatively soon, and hopefully you can compare methods. We'll also put together with it a lot of metrics, because how to compare which method is good for what and when. So we hope that by open sourcing this, we don't solve the problem necessarily, but we are the beginning of a problem solving a solution. And we hope that many of you, especially the ones among you that are outside our area, will contribute to it and guide us. Yeah. Then I want to say one more thing, which is something that I'm very interested in, and if any of you has interest in that, I'd be keen to discuss, which is in many domains, this observational data with interventions is not just collected at random. There are experts making some judgments. So this notion of expertise, correct expertise, I have many clinicians who believe that their fellow colleagues don't know what they are doing, and some who feel differently about it. So increasingly, we are starting to look using machine learning methods, because that's what we know, but I'm sure that you may have a different perspective from your field. Try to really understand why a certain choice has been made, and trying really to understand and quantify this expertise, both to be able to correct maybe misconceptions or understand variation in practice that's desired and separate it from undesired variation in practice. So this notion of these biases, we often talk about biases, but these biases may be actually very good biases, maybe expertise. So we have a relatively recent machine learning paper at iClear where we try to look at these biases and the value of expertise. And if you are interested in that, please reach out, because I need new ways to think about this problem.
Okay. Sorry. Thank you, Michaela. I wonder whether there are questions from the audience. Maybe I have one first question for Julie. You said earlier that you were exploring the use of contextual effects, and I think this is something quite challenging and very informative. And you said that their use would definitely help the interpretability of your results. And I was wondering whether these, whether this was challenging to model the contextual effects. And so any reflection would be good.
Yeah, I think it's... Yeah. Oh, okay. No, I think it's extremely challenging, and it takes a lot of time really to try a lot of discussion with the clinicians. And even at some point, I feel that I understand how they collect data and what the data are. And in fact, after other discussions, I discover new things. And to model it, for now, it's really a bit case study by case study. Like, okay, when they say, like, for instance, for this distributional shift, I say, okay, maybe I can just add that there is a new regulation, like as a new feature. But it's really like on a basis, I will say. Like, I have not like a generic solution or recipe to do this.
Michaela, do you have an opinion on these?
So I'm not sure it's exactly on point, but I have some thoughts about something that I'm very interested in, which is not for the causal case, but for the predictive case. We are very interested to determine what's the minimum information. So these methods are wonderful for trying to understand, trying to really understand causal effects. But if it is to apply it now in the era of personalized medicine, I don't want to measure everything under the sun about this individual. I'd like to measure the minimum amount of information to know how to treat. So going back to prediction, I've been looking for quite some time to this issue of what is the minimum information I need to know about this person to do some time to event analysis, for instance. And do active sensing, active learning in both the static as well as dynamic setting for competing risks, for instance. And very recently, we started to look at that in the process of causality, and we have some interesting first results. And I think it's interesting. So it starts to be interesting to determine for the individual, given whatever information you have about them, at the time you need to make a decision, how would you measure the next things to determine how to treat this person? You have done maybe a diagnosis, but now. So this is not exactly on point, but it's something that we are just finalizing around this area.
Yes, maybe I will add that taking into the context for me is maybe a bit more for predictive models as well. Sorry. It's important because often the clinicians I'm working on, they are interested a lot in generalizability, in the sense of external validity, to see, is it going to be generalizable to other population? But for some predictive methods, and depending on your objective, I just don't want to generalize in other hospitals. I want something which works in my hospital with taking into account all the organizational context, which will be completely different from one hospital to another, because they have different practices, different people. And so if you want to implement something for your hospital, you need to take your constraint. So the focus on generalizability sometimes for me is a bit too much. Like you want to generalize to have maybe some recipes that you can generalize, but not everything. Because if you want something to be useful, you need to take into account what the device you have to collect the data, how the teams are organized and work together, and this kind of things.
This is just a very, very open-ended question for both of you. In these healthcare settings, a lot of data, we have some of it is structured and then it's nice, and but a lot of data we have access to is just free form, doctor notes, that kind of stuff. And often there's this idea that a promise of using machine learning in these kinds of settings would be to be able to incorporate this unstructured data into a causal analysis, for example, by controlling for it. So I was just curious on your take on kind of where we're at in doing this, what we're able to do, what the challenges are.
Yes, I agree with you that there are a lot of hope for this. And for all the things that I have seen now with the hospitals that I'm working on, we are a bit far, at least, to really use this data, because I think there are still a lot of technical issues to be really able to exploit this data. So yeah, I have had access at some point to data that comes from text, automatically written, blah, blah. But we need to spend so much time really on kind of post-processing this data to be able to use it and to recode it, that for me it was not yet like something that I can use easily. But,
I'm the machine learner. And I'm very excited about that. I think, like you say, there is a lot of opportunity there. I think the large language models are a godsend for us, also to help us a lot on that. I don't think it's per se very easy, but there are some interesting approaches. Some of them come from David Sontag's group at MIT. They've looked at some related things. Maybe Yuri can say more about that. I think there is an enormous opportunity to use this clinical data, if you have it, to inform you about the context, to inform you about missingness, informative missingness, maybe some things about the reason behind being given a particular medication and the thinking of the clinician, such that you understand the clinical context that has led to that. So again, I'm very interested in assignment. Why somebody has reasoned in this way to assign this variable, this treatment to this individual? And why this moment in time? And why not something else? So these clinical notes often provide some reason behind why a particular choice was made. So I think there's an enormous opportunity. I think that with the help of large language models, we can do a lot more of that and easier. So I'm excited. I'm excited. Yeah.
So a note on that. I think maybe Jali remembers that, but there was recently a PhD thesis at Harvard Statistics Department. I think it was Regan Rose, now Regan Moser, because she married, and you know, in the US you have this habit of getting the last name of your husband, but anyway. And she, in fact, used text data to generate both covariates but also outcomes. And also a comment on what Michela said about having softwares that, you know, includes and allows you to implement and use the different machine learning tools. Of course, this is good news, but at the same time, bad news, I would say, because we are essentially trained of, even in observational settings, to essentially pick the methods according to a quasi-protocol without having access to the outcome. And so the temptation when you have such a huge softwares that are doing anything for you is to, applying whatever is, and looking at the answers and maybe pick the methods that gives you the answer you want. So we are a little bit back to also the comment that Dimitri made this morning, that this credibility revolution was, a feature of it was also to concentrate on design and also observational study and focus on the assignment mechanism and also on the assumptions. And then here, once you have all these methods that are creating tons of answers, and there is not a clear way of picking the answer that it's consistent with the assumptions and everything, that's a problem.
I'd like to respond.
Yes.
So I completely agree with you, but actually I'd say there is a solution to it. I invite as many of you that are interested in this to help us build on top of these many methods the right guardrails and the right way of interaction with the practitioner, such that you bring the know-how that your community has to the practitioner, such that they can think about these issues. So I'm not just proposing we have this package, we give it to a clinician, and we say, good luck, take the best method, and which one gets the best precision estimating of heterogeneous effects, take that one. I'm not saying that. Maybe there is an opportunity to build, if you like, a set of principles and guardrails to allow the practitioner to think about the different issues associated with taking these methods to their data. And I think that can be done in an unbelievably much easier way now that we have large language models. So I think there is an opportunity to bring the know-how that the econometrics, the statistics community has built over years in many papers, many points of view. I think it's an opportunity to capitalize on that and build not only the methods, but also the know-how into something that's accessible to a practitioner. And I think that becomes really possible. We build, as we speak, a lot of co-pilots. We are excited about large language models and the co-pilots that we can build for clinicians. And I think that such know-how that exists could be very nicely encapsulated to accompany the software that can do everything, but maybe wrongly. So I think it's an opportunity for anyone interested to really help the practical world to bring this know-how and distill them in ways in which, I don't know whether I'm clear what I'm saying. So right now, the way you would, as a practitioner, first, you probably cannot code, yeah, because none of the clinicians can code. Many of them can't. There is a minority that can. So, and they shouldn't. So what will they do? They will knock, no, I agree with you. So they will knock at the door of the next door machine learner or statistician or whoever they can find. That person may be very knowledgeable or much less knowledgeable. So there are all sorts of issues associated with it. So the opportunity is to build these, if you like, co-pilots to help the practitioners with all the know-how that a community, such as the statistical community, has accumulated, to put these assumptions, this know-how on top of the methods, such that there is a discussion that's happening not with the person next door, which may be fabulous or horrible in terms of knowledge, but rather with the entire know-how of the community. So I'm very excited about that, because that can really, I think, speed up adoption. Right now, these conversations happen one conversation at a time between a practitioner and somebody who may know that statistical knowledge. I'd love to have access to Guido's head on a daily basis. I have many questions that I wish he and many others of you will have. And maybe in this way we can brain dump his knowledge and then through a large language model can access it by taking all the papers that he has written and maybe interacting with him personally to allow us this type of knowledge. I know this sounds a little bit maybe controversial, but since it's a panel. So I think I'm quite excited about this aspect because it may help us bridge the more practical world of machine learning, where we like algorithms, the more careful way of thinking that exists in econometrics, in statistics, and maybe we can bring them together and offer co-pilots that are both algorithmically savvy and much more careful about assumptions, about variables, about ways of thinking that your community has developed. So maybe there is an opportunity, and if you are interested in that again, keen to discuss more.
Anybody else?
You need to respond to this.
I feel compelled to say something. So I think it's very interesting to have this interaction between these algorithms for causal discovery and try to bring in expert knowledge. And it's sort of clear that could actually be much better than just relying on the algorithms. It is very clear that the experts know a lot. It shows up in what data they're actually collecting, and so there's a lot of information that isn't accessible directly to these algorithms. But at the same time, of course, the experts miss a lot. There's a lot of things they think they know, but they don't. And so there's also a lot of danger in just building that into these algorithms and then not allowing them to actually come up with very surprising things. And there's a lot of these examples where the experts all thought one thing was going to be true, and actually it turned out that wasn't true. And you kind of need to find ways of still making things open to that. But sort of how you balance those two things, I don't know. So I think that this is a very interesting area, but there's going to be a lot of challenges.
Again, if I may jump into that, this is why we started to look at what we call expertise, trying to understand expertise, inverse expertise. We are building some new ideas that go beyond inverse reinforcement learning, trying really not to replicate what people do, but rather to understand why they are doing that, and trying to look at this bias, this is why they make a decision, and what is really expertise, what's bias, what's sustainable, what's not. And again, we publish in conferences, Fast Food Nation. So this is an iClear paper that we published this year, trying to build some ideas from inverse reinforcement learning with ideas from causality to exactly try to think about what you say, because many of the good clinicians acknowledge that. They acknowledge that they are doing something either because it was taught to them in this way or because some guidelines are advocating for that, while other clinicians are much more adventurous at times and disobey even some of these guidelines if they believe there is a good reason to do so and then have a hunch. So I think that we need some new set of methods to try to understand why these decisions have been made. And I think it's especially interesting in settings where the decision maker had some expertise, has at least some hunch. So I think that that's an interesting.
Yes, I can continue on this. I just continue on this because I fully agree that the knowledge that they do a lot of mistakes. I work with ICU clinicians, and they told me that all the time the trials they run leads to negative results. So they expect to see the effect of a drug, of an intervention, and each time they run a trial to assess this, it's completely wrong. So in fact, I feel sometimes I just release on their graphical model, and which can be completely wrong. And when I was mentioning like combining expert and algorithm, I have not put a lot of thought on how to do this, but I really feel the need for this. I was thinking more about something a bit Bayesian, like with an a priori, like I just have my a priori that I want to incorporate and see what we can do with it.
Can I just chime in with a small, just for the context? So suppose what you guys are discussing now, and Guido as well says, is correct. So either the doctors sometimes do something worse than what you can learn from the data at hand, or they might do something better. Like, suppose you go then to an observational data set, like the one Julie presented together with the trial. Then you know there's unmeasured confounding in that trial, because the doctor used something you didn't measure in your data set. So which means that the results you gave are actually invalid. So you cannot know if those results are due to unmeasured confounding, or if there is a real difference between the trial and the observational data in that setting. So I'm just pointing to the issue. Whenever the doctor has extra information, there's unmeasured confounding in your data. You cannot analyze them with the usual method.
And this is maybe where this other point that was made about the patient notes, maybe there is some information also about that in the patient notes.
Hopefully, but there's a lot they don't write down. I mean, they look at the face of the patient. They look at their history of seeing that person before. They have sensitive information.
Yes, on that point, that's why having other methods, like you can just work with the observational data, but I also have like the generalization methods that have other assumptions. So maybe like with my observational data, okay, I have unmeasured confounding, I have missing values, But then when I generalize, I have other sets of assumptions. So then it's just a matter of which assumption you trust more. And it's just slight evidences on the effect with different techniques and assumptions, I would say.
Thank you. This is a really interesting discussion. I was kind of thinking about two questions. One is they're both kind of slightly outside of the exact the points that everyone is making, but I was kind of wondering about the kind of trust or acceptability that patients have in these systems as they get more popular. So there's a lot of, it's a very diverse set of opinions about AI in general or machine learning. And in different contexts, people have different levels of trust. I think, generally speaking, it's probably a little higher in health than it is in like self-driving cars. But there is maybe some people that are still skeptical. And I wonder how do you think that the kinds of machine learning techniques and the kinds of automated things that are going on that either are going to replace or augment doctors in this way, did have the level of trust that need to happen in order for them to truly become to benefit society? Or is there some other step is there something about the doctor being able to explain the reasoning behind a decision to a patient that is important for things like compliance with medication and things like that? So I'm just kind of curious about how do these things get, when they actually get implemented, how that works. And then also, if it were to become like widespread, generally, would it change how we do observational data work on this? If it became the case that there was, every doctor became replaced or was augmented by one of these systems, would we have to do something? This is kind of related to some of the questions just now. Would we have to change something about the way we analyze data? Would it change the kinds of assumptions we need to make in order to evaluate? Do we need to change the system and how that works kind of over the long term? Thanks.
This is an amazing question, and this is a very important conversation that's happening a lot as we speak. So I'll put two hats. First, as a patient. As a patient, let's be honest, if I get diagnosed with something, I'd like to get to the best doctor I can get to. The variation in practice is huge. I lived in 4 countries in my life. I will tell you that I'm very worried about the decision that's made by the person in front of me. Also, I'm coming from a family of clinicians, and I know that going to the best doctor you can find is the most important. So I really hope that, I don't want to go now into a plane without a human pilot and a co-pilot. I personally, as a patient, I would like to have a doctor with a co-pilot. I don't just want to have a doctor. I don't trust even the best of doctors. I'd like to have a doctor with a co-pilot. But this is me, it doesn't need to be you. However, so that's one hat. The second point is we know that these machine learning methods are horribly brittle. At times they are not well debugged. So I want the clinician to understand the decision. I want these methods to be very well, very transparent. That's the reason I increasingly work in methods that are either completely transparent or transparent by design, because I think in medicine that's necessary if we can. I think measures of uncertainty are very important. I think understanding very much your point about the data. How did this model come into being is becoming very important. And of course, there is regulation happening right now in different countries with different types of perspectives about AI as medical device. And I think that way of thinking will need to advance. I think we need to be very transparent on what was the data that was trained on, what type of the assumptions. But I do hope that doctors will not be replaced. However, I do hope that doctors very soon will have co-pilots that they understand and can collaborate with. But as somebody that works a lot with clinicians in different countries, from Italy actually to the United States, to the Netherlands, to UK, there's a very big problem of how to teach these doctors AI and at what level. And even that is very complex. Because should you should you know enough to be able to use this AI system? Should you have enough knowledge to understand that this AI system was indeed conceived under this data, under this regulation, and hence you cannot apply it for the patient in front of you? I think there's a very, very complex set of discussions that we need to have, because in the UK, for instance, we have some regulatory bodies, which I think don't understand that much about neither medicine nor AI. I'm going to leave it at that, such that I don't make too many enemies in the UK. But I think one needs to think very carefully also about that, because having doctors that understand sufficiently about this AI as medical device, I think will be a very complex conversation. But clinicians are very smart people, so I do think that especially new generation of clinicians will become much more savvy in this area. And what I personally hope to achieve is that the clinician will be more in the driver's seat rather than the AI person. And they are going to more or less drive the tools. They are going to build these copilots. That's the reason for me I'm extremely excited about large language models, because it will allow for a lot more without code for the clinicians to be in the driver's seat, to build these methods, to design these methods. This is my thinking on it.
I can just add that when I have designed this clinical decision aid system for the clinicians, in fact, they do not use it to replace them. They just use it as one additional parameter. They are able to handle with a lot. They are very quantitative. They deal with a lot of information. For them, it's just one other that they will take into account in their decision process at the end. And then, regarding the acceptability of the tools, sometimes, in terms of interpretability, it's a bit of debate. Like one clinician will say, I want interpretable things. The other, in fact, I don't care as soon as I know that it works, because I spend my life giving drugs to patients, and I just don't know exactly what's going on. I just know that it works because there have been some trials. So if you assess the tools in the same way that you assess drugs with trials, then they are willing to use things that even they just don't understand. They know it works and it will be helpful. And then regarding the patients, there are a lot of initiatives where you have a like consortium with patients, with clinicians, with researchers to try also to incorporate the patients. And as a patient, if I use my policy learning example, I'm not sure for now that I will be feel very secure in using these methods for now, if it recommends me a dose, so we'll see.
I think there was a question in the back. Yeah.
So I'm going to put on a physician hat, and I hope what I'd like everybody to do is think of themselves as a patient. In all of these conversations, and you talk about, first of all, I want to say, getting the reason for the intervention, the assignment, the treatment assignment, is critical. And I've been arguing for years that that should be a standard part of every study if you're doing an original study. So that is all possible. I don't think it's possible in administrative data. There are too many blocks, and I don't think you'll ever get there. We can talk about just work process and workflow and how that would work. If you can solve that problem, that would be great. I don't think you can. One of the things that everyone's talking about, especially in this, where none of the physicians followed the recommended treatment. Whenever we do a study, they're thinking about treating a disease. But doctors don't treat diseases, they treat patients. And that's what you were saying, is as a patient, you're going to make a decision. So if you sprain your ankle, the best treatment for an athlete is not to cast and not to operate. The best treatment for a pregnant woman or a woman with a 6-month-old baby who has to walk around is to put a cast on, because they can't walk around on crutches for 4 weeks or 6 weeks. So we are always dealing with multiple outcomes, but in the studies we never look at that. And I don't see, maybe you guys can figure out methods to look at all the possible outcomes for all the different patients and all the different ways that they think about it. So I think when we do the research, we advance knowledge for some things, but we should recognize that that's still not the same as treating patients. And anyway, so there's a lot more discussion on all those points. But just think of yourself as a patient every time you're doing a study. And most of the statisticians I work don't. And then when we bring it back, when we bring that to them, they start to understand, okay, now we have to do it this way and that way. And it changes the way they approach the problem.
I love it. I agree. I understand. So we should try our best to solve these challenges, even if it's a little bit. Again, one thing that we have been looking at and build some methods on, again, we are machine learners, we like to build methods, was for treatment effects for competing risks. So we tried to look at this problem where we knew that the data set had patients that had multiple competing risks and multiple comorbidities actually at the time the data was acquired, and tried to think how can we do treatment effect estimation and how do we deal with heterogeneity of treatment effects in settings with competing risks. We dealt with that as a machine learning problem, so we came up with some results. But I kind of completely understand that probably we don't have one data set that will be enough. But my question to you back would be, what if we get multiple data sets which were collected potentially for the same type of general disease, but with different types of kind of designs, and we combine this data? Could that maybe go a step in solving what you are describing?
We can talk after. I don't think it's enough. We can talk later, but I don't think it's enough. Part of my research is in evidence synthesis, and I think it's super important to triangulate data across different data sets and different questions and different contexts. All of that is super important. I don't think it's enough, though, but that's a more nuanced discussion.
For some reasons, I had predicted your answer. Anything more? No, I think it's been an excellent discussion. I just want to re-emphasize this multidisciplinarity of the Congress, of the Symposium. I think it's been great. There were concerns. Of course, it's not easy. I think there was a lot of heterogeneity within one single session here, because the three of us are very heterogeneous in a way, but still there was, the speakers managed to convey and talk, and then I particularly appreciate your humble spirit of questioning everything you do. You want to have knowledge from clinicians and learn from them, and then probably they offer the help with the tools they develop, and then this was both the case. I'm curious to know later whether you show your results of the discrepancy of the Sankey to MDs, and I'm very curious about what a French doctor would react about this discrepancy. But then, once again, I think this stresses the need of developing a common language, that we need to understand each other. This is not easy, and then the science progresses if we be all of us on the same page. And with that, please join me in thanking the speaker.
Thank you very much. And as mentioned before, it's time for this important announcement. So Jolie Meng, professor of statistics at Harvard, is gonna make the announcement as editor-in-chief of the Harvard Data Science Review Journal.
Thank you. I should have some slides there. Just, if you can put it together. Well, as we're setting the slides, I just want to say one thing to echo the doctor at the back. I think the one really important issue that we, in the machine learning statistics, we do not emphasize that much, which in other fields, people emphasize a lot is this whole notion called a contextual integrity. This is the work by a philosopher, Helen Nissenbaum in the field of data privacy, right? So you always need to think about the context. And it is, I think it's exactly your point about thinking about different context, you will change the answer. But I think the fundamental issue is really, which is quite related to what I'm going to talk about, is really that machine learning or statistics, broadly speaking, fundamentally is about a pattern recognition. You need enough replications. So I think the one thing we should be all aware of, we shouldn't be that ambitious, we're going to solve all the problems. It can't. It's basically, if something is truly individual, and how would you learn? And that becomes a philosophical question, right? What is individuality? What's a universality? I think, the thing I love about conference or workshop like this is just a very broad spectrum. And I think that's for the one big reasons, when I heard from Fabrizia and also Francesca about doing this conference, I say, hey, we want to publish something on this kind of very broad discussion because we all enjoy small conferences like this, but the one limitation of small conferences is whatever we say here, we all enjoy very much, others do not necessarily benefit from them. So what we create this forum, what we call the Harvard Data Science Review, is we call everything data science for everyone. And I want to give you some examples what we're doing here, and I also have a little game for you to play. So you prepare to stay here for 2 hours. No, I'm kidding. And I want everybody to contribute. I think you have writing to people about different format. The idea is that can we bring conversation like this to benefit a lot more people out there by reading it, by maybe have videos, so on and so forth. So this was created in 2019 and was really modeled after Harvard Business Review and Harvard Law Review. They have the big brand name, and their brand name is very big because, whenever I say Harvard Data Science Review, nobody knows what that is. When I say it's a sister journal of Harvard Business Review, they say, oh yeah, I understand. Even those people have never read Harvard Business Review. You see that brand name is very important. And we did do very well. We got the award of Best New Journal of Science, Technology, and Medicine by this supposedly to be a very big publication association in the US. And so what I want to show you is, first, just very quickly, to encourage you to publish in HDSR, if I ever get this thing to move. Next slide. Okay. All right, so by now, we publish 4 issues a year. We have done, because 5 years, we just celebrated the big 5-year anniversary, we have done 20 regular issues, 5 special issues, 3 printed issues. I have a couple of printed copies right here. And we do special themes. We have articles, commentary, rejoinder. That's the one we're going to get you guys involved. Interviews, including panel papers, which I think it's innovation. It's very much take the panel version, oral panel version, translate that into a paper version. You read like multiple people have the conversations. And we really emphasize international outreach. We have authorship from more than 30 countries. We certainly like to have a lot more than 30 countries because there are like 200 some countries. And we also do a monthly podcast. At this, we have the 44th episode. I want to mention is that in the next few days, probably even today or tomorrow, we'll be launching a new podcast, and that one is squarely on causal inference, just by coincidence. But guess what? What would be the topic? What's the topic? What's a popular topic that causal inference is incredibly important? Not medicine, not education. Any guess? Climate change will be one, yes, but climate change is a heavy topic. This is a much light topic people likes, although probably not in this country. I can tell you, sports. Which sports? Football, yes. Not soccer, okay, sorry. And so we had the head of data scientists from NFL to talk about the and he's a specialist in causal inference. That's another person you can invite next time. And for them, right, it's very interesting. The word causal means what? To him, and it's like any practical problem means that whatever I do, in the end, I want to see a change. That's what matters, right? And if you think about no matter what study you do, whenever you implement something, you think it's going to make a change, you are making a causal statement. Or at least you hope it's causal, right? So they really talk about all the NF regulations. Whatever they do this month, it's going to probably change the things in the next season, hopefully. And if it doesn't change, they just redo it. So, right? So squarely, it's about causal inference. So usually here, I thought it was just such a coincidence. And let's see if I can get to the next ones. this is a problem I want everyone to help me to solve, because, as a data scientist, as a data science journal, we're supposed to should be driven by data. I tell you that I'm not driven by data at all, because I do not know how to collect data about a readership. Okay? We have these statistics like 3.2 million page review views, but what does it mean? That means very little, right? And we have this unique download, so on and so forth. I first got excited, and then eventually I learned this from MIT Press. We team with them. Whenever I say unique download, then they trace the IP address. Now, anytime you change you clean your cookies or you change your device, that's another IP address. So I have no idea how many people are actually reading. And then I even think about, what is a readership? That's actually a really big question, measurement questions. How do you measure somebody's reading, right? Is it browsing reading, 2 minutes reading, diving to reading, like how do you measure reading? Those things are incredibly important, talking about making causal inference, because I wanted to do things that can increase the readership, right? Or increase authorship, but I have no idea how to do that. So I put that as a challenging problem for this crowd. But I have a tease for you. Not surprisingly, we have, well, actually, I was very happy to see 2/3 of readership is outside United States. All right? And this is the funny one, because I always tease people. A year ago, I would be teasing people. MIT Press traced, there's one thing I do trust, which they trace where the IP address come from. That's kind of hard to fake. You can always do it, but mostly I don't think the reader's faking on that. They traced about 235, 236 areas, regions, countries in the world. That's all of them. We were getting every one of them except one until last June. Can you guess which one's that? Just one. We got everywhere we have readership, which I'm very proud, but there's one place we just could not get it until a year ago. What? Who said Vatican? Great. Yes, that's the one. Okay? So, Vatican City. But then we discovered Vatican City. Suddenly, there were 2 IP addresses coming. And for me, I said, that proves that even God needs an assistant. It can't be great. Anyway, so now we have from everywhere. Okay, so that's just the one thing. We started a new causal column, and with 2 co-editors, Yav and Francesca, and none of them are here. See, they disappeared. Okay. And they wrote a bunch of articles, so on and so forth. So the column itself is for these kind of conversations, and there's articles on a causal inference. But I want to really tell you about this particular format, about discussion article, and I'm hoping to get a few discussion articles from this group. And this is a little game we'll be going to play. Just look at, so how many people know Dave Donahoe in the sense that you know who he is and you know what profession he belongs to? Quite a bit, right? Okay. Now, this is a discussion paper. Many statisticians are very good at do discussion papers. Interestingly, that's not much in computer science or in other fields. When I ask them discussion papers, what does it mean? Now, when we do discussion articles, we do not just ask a statistician. That would defeat the purpose. The whole idea is to get people from all kinds of different fields. So here's the game I want us to play. Look at all these discussions. I hope for it you can see them. All right, and I just take a look, and I want you to think about how many of them you actually know. You know them in the very minimum, right? If they're statisticians or computer scientists, or roughly what they do. All right, just take a quick look. And I know one of you even married to one of the authors here, right? I just learned. So you see how broad we reach out, All right. So I want to see a show of hand. How many of you can claim, and I hope you are not lying, you know more than 3 authors, including being 3? Okay. That's pretty good. 4. How many have 4? This is a very 5. I'm gonna, like auction, I'm gonna keep going. 5. How many hands left? 3. Well, you're married to one of them, it doesn't count. Oh, no, just kidding. Okay, so there's only 3. How many? 6. All right, okay. So here I got 7. I'm gonna keep going. Oh, this guy knows there's so much. 8. All right. Well, the idea is you probably still, even 8, you know less than half of it, right?
So as you do get a reward, okay? As the first one, you got the 8, and the other 2, you stop like with a 5, right? 7? Okay. All right, so for the 7 one, you're going to get a signed copy from me. And you can sell it on eBay, but make sure I can no longer sign before you sell it, okay? And for the other 2, this is the inaugural issue, which contains lots of articles. This is a special issue we just published, another great topic, called the democratizing data. What does it mean? How do we let the public to collect the data? And it's a lot of fascinating machine learning problems, social problems, all kinds of problems. And these 2 go to the next 2 winners, wherever you are. And I will sign up for you as well. Okay? So the whole idea is that I hope that these articles we have, for example, the great talks we have here today, some of you will be willing to write this thing, and my job is, the best part of creating this journal is I now know lots of people across many fields. Because my board itself overall has about 150 people, from editorial to the advisory board. And the board members we have literally from philosophers to quantum physicists, right? Because that's the press. And I think we're trying to get all these different people discuss the article. I hope we have a very rigorous, the review process, because the other really interesting thing. Today we talk quite a bit about the difference between qualitative study and the quantitative study. I tell you the challenge I have as editor is how do I ensure the papers will pass, a qualitative paper will pass a high bar for the quantitative people and vice versa. There has been lots of challenges because people from either side will say, well, where are the data? They're only arguing philosophically. I want to see the data, and the other side would be saying, yeah, there's all formulas, but where's the context, right? And so it has been incredible. And I hope that whoever wants, I hope you would be willing to write, and this way that we can get people to react and really push together the whole human inquiries really requires everything, right? Not just one side versus the other side. So my last slides, I won't take it 2 hours. Okay. My last slides is really just to tell you the 10 ways we publish in HDSR. And I'm hoping this conference itself will generating at least a discussion article and the panel articles, but there are other ways. So I want to just show you what these 10 ways. The first, as I said, is we do special issues, which are the 12 to 20 articles. That's special issues. We do special themes. The only difference is special issues published anytime by itself. Special themes is within the regular publications. There are pros and cons, but it requires less. I think we're thinking about more like a special theme, right? And we do discussion articles, okay? So this is one I already showed you an example. We do these are regular articles, and the regular articles we have 4 sections. Panorama is about the vision, debate, overviews. Cornucopia is about transform knowledge applications. These are like, you're not creating new methods, but you have impact work by using existing methods. Stepping stones are all about data science education. But what's very important is for we do this journal is we want to do research, we want the education, we want the public impact. So I tell people it's 3 in 1, right? It's a research journal, education publication, and it's a popular magazine. Everybody told me, like, you cannot do that. I said, that's exactly not what I want to do, right? And with the HDSI supported with everybody help, I think, you take a look. It's entirely free, okay? There's no charge to you. And that's 4. Then the millstone is where we publish these high-end theoretical articles. I think Jose has one there on causal inference. That's where you will see as many formulas as end of statistics. Okay, any codes, whatever it is, it's a foundational one. But that one is also, that's one actually we competed with others for these paper. And then we have these columns. Columns, we have dive into data. This is for the general, this is like tutorial. Active industrial learning is for the industry. Effective policy learning is for the government. Mining the past. Mining the past is a really fun one. It's the history of data science and AI. And we have the 2 co-editors are historian of science. And they really know what they're talking about. And the Mining the Future is for K-12. I think K-12 probably doesn't mean anything. Elementary to whatever, secondary. These are for the future. Regression randomness is for the general public. We have like how do you search for the recipes, how do you does computer write a poem, wines, all the stuff. That is reinforcing reproducibility and replicability is the one that you all understand the social sciences. That's a very important question. The new one actually, now I see this is actually should be put in, is that causal section, which is the newest one. Actually, we missed another one. We now create a new column by two philosophers, Causality philosophers, called the metadata science. It's about a philosophy of data science. The first column is talking about between frequentist and the Bayesians, there are 5 different flavors. You should read that one. It's online as well. Okay. And we write, then we have these shorter essays. Sometimes the things you don't have to talk too much like me, you talk very short. And then there's all kinds of interesting conference announcements. That's a short essay. And then we have these interview articles. The one thing we discovered that if you want to engage like government leaders or industry leaders, they don't write articles. They have no time, but they love to talk. You just interview them for an hour, Zoom, then you do the transcript, and then you let them approve, their team approve, and that's actually readers like to read them too. It's just a conversation, but it's a written version, right? So that's a format. It's important. And then this one we invented during the COVID time. We want to get expert opinions very quickly. Nobody was having time to write. I had one editorial member, David Banks, some of you know, a statistician. I said, David, organize this. So he get a bunch of people and having 1 hour Zoom, and he basically writes up all the conversations, but not writing as a one piece, but rather from each individual. So I'm thinking this one, probably the panel discussion here. Do not write it as a coherent piece, because it's not coherent. Readers will not like it. But if you write it as the conversation, dialogues, people know what to expect. And that's very, very important. Then we have a conversation with leaders, which I already talked to you about. The conversation with leaders is all the industry leaders, government leaders, academic leaders. Then we also have a conversation with authors. Sometimes you write an article, there's a whole story behind it. The one conversation we had was with Bing Yu, that she did an incredible paper about her COVID-19 experience, how they set up everything, collecting data. But there's a story itself is way too long for the paper. So we did a conversation and published together, so you will read those things together. I hope this is enough to entice you to write something. So thank you very much.